Welcome to Math 21 discussion class on rectilinear motion and more antiderivatives. So for today, first we will be reviewing the important formulas and concepts for this class, and then we will be solving rectilinear motion problems, and then we will be solving integrals. So let's start with review of important formulas and concepts. So for this class, recall from rectilinear motion that we have three important functions: the position function, the velocity function, and the acceleration function. And remember from LE3 that the derivative of position is velocity and the derivative of velocity is acceleration. So now with integration, we can reverse the process. An antiderivative of acceleration is velocity and an antiderivative of velocity is position. And they are particular antiderivatives. So that's enough for rectilinear motion. For integrals, we have many new formulas here. Most notably, we can now integrate 1 over u, or u to the minus 1. We couldn't do that before. Similarly, we can now integrate exponentials and the other four trigonometric functions. Okay, that's enough review. Let's dive right into the problems. Let's start with rectilinear motion. Let's do our first problem. This is at the module, page 207, D1. A ball is thrown vertically upwards from a platform 8 feet above the ground. After 2 seconds, the ball is 2 feet below the platform. Find the initial velocity of the ball. Assume acceleration due to gravity is negative 32 feet per second squared. If you want to solve this problem first before looking at the solution, you may pause the video now. I'll give you 5 seconds. Okay, let's look at the solution. First, we have a of t, which is the acceleration, to be negative 32 because we will assume that only gravity will affect the ball. So that's a of t. But what do we need? We need the initial velocity of the ball. That means we need to find v of t. But how do we get v of t? By integrating a of t. So v of t is the integral of negative 32 dt. And you already know how to do this. This is just negative 32t plus c1. Now let's also get the position function. The position function is obtained by integrating the velocity function. So s of t, the position function, is the integral of negative 32t plus c1 dt. And you know how to integrate this as well. This is just negative 16t squared plus c1t plus c2. But we want to find the initial velocity, so we need to find c1. But what are we given here? We're given positions. The initial position is 8. And then after 2 seconds, the position is 2 feet below the platform, which is 8 feet above the ground. So the position will be 6. So with that said, we will have to solve for C2 first. So let's solve for C1 and C2. The initial conditions are, as I've said a while ago, S0 equals 8 because of the platform. And then S2 is 6 because after 2 seconds, the ball is 2 feet below the platform. So let's solve first. S0 equals 8. But S0 is just C2. So C2 is 8. So therefore, S of t is negative 16t squared plus C1t plus 8. And let's solve for S2 equals 6 this time. We will substitute t equals 2. So we will get negative 64 plus 2c1 equals 8. And solving for c1 here gives you c1 is 35. So Vt is negative 32t plus 35. Now, what is the initial velocity? Initial velocity is obtained by substituting t equals 0 into v, so just have 35 feet per second. That is the final answer. So let's take a moment to take in the solution. Let's go to our next problem, page 207, D2. If the brakes on a car can give the car a constant negative acceleration of 8 meters per second squared, what is the maximum speed it can go to be able to stop within 25 meters after the brake is applied? If you want to solve the problem first, you may pause the video. I'll give you 5 seconds. Okay, let's look at the solution. First of all, we have a of t. The acceleration will be negative 8. Next, let us compute the velocity and the position functions. So v of t is obtained by integrating a of t. or v of t is the integral of negative 8 dt. And you already know how to do this. This is just negative 8t plus c1. Why is there a 1 on the c? Because I will be integrating this again and I will have another constant. That's why I need the c1 to distinguish it from the new constant later. Now let's get s of t, which is the position function. S of t is obtained by integrating v of t, or integral of negative 8t plus c sub 1 dt. And this is just a polynomial, so we can evaluate it quickly. We will get s of t is negative 4t squared plus c sub 1 times t plus the new constant c sub 2. Now, as I've said a while ago, v of t and s of t are cases of particular antiderivatives. In other words, we want to solve for the values of c sub 1 and c sub 2. So we will look at the problem again. What are we given here? We want the car to stop within 25 meters after the brake is applied. There is no indication of position, but there is a distance traveled. So that means we may assume that the initial position is 0 so that it's easy to compute. But initial position is the same as S of 0. So S of 0, we want it to be 0, but S of 0 is C2. So C2 is just 0. So let's substitute the value of C2 into S of t. So S of t is negative 4 t1 squared plus c1 t. Now, we want the car to stop. What does it mean to stop? Means velocity is 0. So we want to know the time when the car will stop. So let's solve this equation. Negative 8t plus c1 equals 0. Solving for t gives you c1 over 8. In particular, this tells us that t must be positive and c1 must also be positive because you cannot have negative time here. So at time t equals c1 over 8, the car will stop. And let's go back. What do we want here? We want the car to stop within 25 meters after the brake is applied. So the position at time when the car stops, which is c1 over 8, must be 25. So at time t equals c1 over 8, the car must travel 25 meters. And that explains this equation. S of c1 over 8 equals 25. But what is S of t again? S of t is negative 4t squared plus c sub 1 t. So we substitute t equals c sub 1 over 8 to obtain the left-hand side as negative 4 times the quantity of c sub 1 over 8 squared plus c sub 1 times the quantity c sub 1 over 8 equals 25. Let's just simplify the left-hand side by expanding and combining fractions. So just verify that the left-hand side simplifies to c sub 1 squared over 16. So c sub 1 squared over 16 equals 25 simplifies to c sub 1 squared is 400 and taking square roots gives you c sub 1 is plus minus 20. But as I've said a while ago, c sub 1 is positive. So we will take c sub 1 equals 20. So that means that v of t is negative 8t plus 20, which is linear with negative slope. That means that the maximum velocity will be obtained when t is smallest. So maximum speed is v sub 0, which is 20 meters per second. And that is the answer that we want. Okay, let's take a few moments to take it all in. And let's move on to integrals. In this discussion video, I will be discussing the solutions to 12 integrals. They will be on the screen now. Let's take a moment here to pause and take a screenshot for your reference later. Okay, ready? Let's dive in to the first problem. Integral of x squared minus x over 1 plus 3x squared minus 2x cubed dx. If you want, you can pause the video right now to solve the problem first before looking at the solution. I'll give you 5 seconds. Okay, let's solve it. First, notice that the integrand is a complicated fraction. So most likely it will not look like any of the formulas, but we have the power of U-substitution to simplify the integrand. So let's look for a target for the U or a candidate for the U. one tip in looking for the u in the u-substitution is to look for a part of the function whose derivative also appears in that function as a factor, or probably when you multiply it by a constant. So here, notice that the denominator 1 plus 3x squared minus 2x cubed has derivative 6x minus 6x squared. And we have x squared minus x, which is negative 1/6 of 6x minus 6x squared. So that means that we will take our u to be 1 plus 3x squared minus 2x cubed. And of course, as I've said a while ago, du is 6x minus 6x squared dx. And x squared minus x dx is negative 1/6 du. We just factor out the negative 6 from the right-hand side in the second equation there. Our integral now becomes, the denominator just becomes u. And the x squared minus x dx becomes negative 1/6 du. Now, we can evaluate this integral. We just have a constant, negative 1/6 times 1 over u as the integrand. And you can just copy the constant later on when you integrate. So, we will just integrate 1 over u, and then later on multiply the negative 1/6. The integral of 1 over u is ln of absolute value of u plus c by the formula a while ago. So, the integral of 1 over u times negative 1/6 du is negative 1/6 ln of absolute value of u plus c. But we're not done here because we have to substitute back into x. That's because our original integral is in terms of the variable x, not the variable u. So, we will just use our substitution rule. So, negative 1/6 ln of absolute value of u plus c is equal to negative 1/6 ln of absolute value of 1 plus 3x squared minus 2x cubed plus c. And that is our final answer. So let's take a moment, take it all in before we move on to the next problem. Ready? Let's go to the next one. Integral of 3x to the fifth minus 2x cubed plus 5x squared minus 2 all over x cubed plus 1 dx. Once again, if you want to solve this problem first without looking at the solution, you can pause it now. I'll give you 5 seconds. Okay, let's look at the solution. This fraction is more intimidating than the previous problem because you have a fifth power and so many terms in the numerator. Let's try a u substitution first. You have two candidates, either the numerator or the denominator is u. But upon checking, well, the derivative of the numerator is not the denominator times a constant and vice versa. So, we can't use the u substitution as of yet, but no problem. Let us use long division first. Just verify this on your own. The fraction is also equal to 3x squared minus 2 plus 2x squared over x cubed plus 1 dx. Look at the form of the function right now. This 3x squared minus 2 is polynomial, and then we have a fraction. X cubed plus 1 has derivative 3x squared. So, we can now use u substitution on the fraction. But what about this annoying polynomial? No problem. I can write the integral like this. I can separate the function. So, I will have two integrals. The integral of 3x squared minus 2 dx, which is easily evaluated using the power rule for integration. And the second integral is the integral of 2x squared over x cubed plus 1 dx. Let's use what I said a while ago. Let's use u substitution on the second integral, letting u be x cubed plus 1 because du is 3x squared dx. And we have the 2x squared dx in the numerator. So 2x squared dx is equal to 2/3 du. And the integral now becomes, the first integral is easily integrated, x cubed minus 2x. The second integral becomes 1 over u, and then 2x squared dx there becomes 2/3 du. All you have to do now is to evaluate what is integral of 1 over u times 2/3 du. And this is similar to the first problem. 2/3 is a constant. We can just copy that later. We will evaluate 1 over u du, which is ln of absolute value of u plus c. And that is reflected in the next line. So the integral of 1 over u times 2/3 du is 2/3 ln of absolute value of u plus c. So our integral is x cubed minus 2x plus 2/3 ln of absolute value of u plus c. But wait, Don't forget that our integral is in terms of the variable x, not the variable u. So we have to substitute back u into x. U is x cubed plus 1 by our substitution rule. So our final answer will be x cubed minus 2x plus 2/3 ln of absolute value of x cubed plus 1 plus c. Don't forget to substitute back the u into the original variable when you integrate. Take a moment to digest the solution. Ready? Let's move on to the next problem. Evaluate the integral of log of x squared to the base 4 and then all over x dx. If you want to solve this problem on your own first, then pause the video. I'll give you 5 seconds. Okay, first things first, notice that this is again another fraction, but this time the numerator is not polynomial and we do not have a sort of reverse quotient rule in evaluating integrals of quotients. So the best we can do for now is to try to integrate this by U-substitution. We will look for a candidate for the U. Let's look at the fraction carefully. Log of x squared to base 4 and then all over x. We have log in the numerator. And notice that its derivative is 1 over x times ln of whatever the base is. But ln of a constant base will be constant. So it makes sense to let u be the numerator, log 4 of x squared. So that's what we're gonna do. Let u be the log of x squared to the base 4 and let's evaluate du. Du by chain rule is 2 over x ln 4 dx. Just verify this by yourself using the chain rule. So we have the 2 and the x in the denominator. In other words, we can express 1 over x dx in terms of du. And that's what we're going to do now. 1 over x dx is, let's remove the 2 and the ln 4 here. Put it on the other side. It becomes ln 4 over 2 du. Or simplifying this gives you ln of 2 times du. So 1 over x dx can be expressed in terms of du. And we will now change the integral. So the integral becomes log of x squared to the base 4 is u. And then 1 over x dx becomes ln of 2 du. And again, ln of 2 is just a constant multiplied to a function u. So the integral for u times ln of 2 du is ln of 2 over 2 u squared plus c. Recall, this is just the power rule for integration. We have successfully evaluated the integral. But wait, once again, our integral should be in terms of the variable x. So we will be using the rule for the U-substitution to substitute back into the variable x. So our integral should be ln of 2 over 2 times the quantity of the square of the log of x squared to base 4 plus c. And that is our final answer. Let's take a moment to digest the solution. Ready? Let's move on to the next problem. Integral of cotangent x times cotangent of ln of cosecant x dx. If you want to solve the problem without looking at the solution first, you may pause the video now. You have 5 seconds. Let's solve this integral. The function looks a bit scary because you have cosecant inside ln inside cotangent. But wait, that ln of cosecant x looks familiar. Remember that this appears in one of our formulas before. Integral of cotangent x is negative ln of cosecant x. In other words, the derivative of ln of cosecant x is negative cotangent x. So what is our choice for u? That's right, it's ln of cosecant x because du is negative cotangent x dx, which is this one here. So now, we can cancel this cotangent x by expressing it in terms of du. So cotangent x dx is negative du. And the integral becomes cot of ln of cosecant x becomes cot of u. And then cot of x dx becomes negative du. And this is easily integrated using our formula. Remember that cotangent has integral ln of absolute value of sine. So the integral of cotangent u times negative du is negative ln of absolute value of sine u plus c. Finally, what is our final step? That's right. We will substitute back into x. using the substitution rule. So our final answer will be negative ln of sine of ln of cosecant x plus c. Okay, let's take a moment to digest the solution. Ready? Let's move on to the next problem. Evaluate the integral of 1 over x squared e to the 1 over x dx. If you want to solve the problem first without looking at the solution, you may pause the video now. I'll give you 5 seconds. First, this fraction looks a bit scary. There's an x squared and there's an exponential in the denominator. But notice that we can put the exponential into the numerator. What's the point of doing this? It's so that we can more easily see our U-substitution. So notice that e raised to negative 1 over x is an exponential. So what is its derivative? That's right. Its derivative is self times the derivative of the exponent. But what is the derivative of negative 1 over x? It's 1 over x squared, which is this denominator. So what should our candidate for u be? It should be e to the negative 1 over x. Then du is e to the negative 1 over x times 1 over x squared dx. 1 over x squared is the derivative of negative 1 over x. And notice that this whole thing is just the integrand. So that means by substitution, our integral just becomes integral of du. It's just the integral of 1 du. So the integral is u plus c. And finally, we substitute back u equals e to the negative 1 over x. So the final answer is e to the negative 1 over x plus c. Now let's take a moment to digest the solution. Let's move on to the next problem. Integral of 5 raised to square root of x times e raised to the quantity 5 raised to square root of x all over square root of x dx. If you want to solve the problem before looking at the solution, you may pause the video now. I'll give you 5 seconds. Okay, let's look at the solution. This fraction looks a bit scary because you have two factors in the numerator, both exponentials, and then a square root in the denominator. So it's more difficult than usual to look for the candidate for the U-substitution. Okay, what can we notice in this integral? Notice that an exponential has derivative itself times the derivative of the exponent. So e raised to 5 raised to x has derivative itself, which is here, times the derivative of 5 raised to square root of x. But 5 raised to square root of x is also exponential, so its derivative will be itself, which is here, times the derivative of the exponent square root of x, which is 1 over 2 square root of x. And then, of course, since the base here is 5, which is not e, you will multiply ln of 5, but that's constant. So it has little bearing on the choice for you. So anyway, with that said, the derivative of e raised to 5 raised to square root of x, as I've said a while ago, contains this whole fraction times some constant. So with that said, what is our choice for u? That's right, it's e raised to 5 raised to square root of x. And as I've said a while ago, the derivative du is e raised to 5 raised to square root of x times 5 raised to square root of x all over square root of x times ln of 5 over 2 dx. So this whole integrand appears in du. So we can just solve for 5 raised to square root of x times e raised to 5 raised to square root of x all over square root of x dx in terms of just du. Indeed, it is 2 over ln of 5 du. So the integral becomes, so this whole thing just disappears. It just turns into 2 over ln of 5 du. This is just the integral of a constant function. So it integrates to 2 over ln of 5 times the variable u plus c. And of course, as with the previous problems, what is our final step? That's right. We will have to substitute back into the variable x using the substitution rule. So our final answer will be 2 over ln of 5 e raised to 5 square root of x plus c. Let's take a moment to digest the solution. Ready? Let's move on to the next problem. Integral of the fraction 10 to the 6x plus 1 all over 10 to the 3x dx. If you want to solve this problem first without looking at the solutions, you may pause the video. I will give you 5 seconds. Notice that 10 to the 6x is the square of 10 to the 3x, and it is reflected here. So what is our choice for u? We may choose u to be 3x, so that the exponent here becomes 10 to the u in both exponential expressions. So let u be 3x, du is 3dx, and what happens to the integral? The integral becomes 1/3. This 3 here goes to the denominator. So you got 1/3 times the quantity 10 to the u squared plus 1 over 10 to the u du. And now let's just separate the fraction. So we separate the fraction into two fractions and we distribute the integral. So we get 1/3 times the integral of 10 to the u du plus the integral of 1 over 10 to the u, or the integral of 10 to the minus u du. 10 to the u du can be integrated already, but 10 to the minus u du still needs some work. So let's apply a substitution. V equals negative u. So dv equals negative du. So the whole expression now becomes 1/3 times the quantity integral of 10 to the u du minus integral of 10 to the v dv. Now both integrals can be evaluated directly using the formula for exponential expressions. So you get 1/3 times the quantity 10 to the u over ln 10 minus 10 to the v over ln 10 plus c. Now what do? We have to substitute everything back into the variable x. So v is negative u. Let's substitute back v equals negative u first into the second fraction. 1/3 times the quantity 10 raised to u over ln 10 minus 10 raised to minus u over ln 10 plus c. And finally, u equals 3x. So we will substitute back u equals 3x here. So the final answer is 1/3 times the quantity 10 raised to 3x over ln 10 minus 10 raised to negative 3x over ln 10 plus c. So let's take a moment to digest the solution. Ready? Let's move on to the next problem. Integral of 3 minus 2 raised to x all over 3 raised to x dx. If you want to solve the problem without looking at the solution first, you may do so now. Pause the video. I will give you 5 seconds. First of all, look at the fraction. It's 3 minus 2 raised to x in the numerator. There's a difference. So we will use one of our tools. Remember that we can separate the fraction into two fractions. So that's what we're gonna do. And then separate the integral. So it becomes integral of 3 over 3 raised to x dx minus 2 raised to x over 3 raised to x dx. Why am I doing this? It's because, look, it's way easier to evaluate each integral separately. In what sense? Well, the first integral, the first fraction, simplifies to 3 raised to 1 over 3 raised to x, or 3 raised to 1 minus x. The second fraction, using the law of exponents, becomes 2/3 raised to x. So the second integral is readily integrated. Just use the exponential formula. For the first integral, notice the exponent is just 1 minus x, whose derivative is negative 1, which is constant. So we will use the substitution rule, u equals 1 minus x, to convert the 1 minus x into just the u, so that we can use the exponential formula. And again, du equals negative dx, so we have the negative sign goes outside here. So the first integral becomes 3 raised to u du with the negative sign outside. The second integral, we can integrate directly. Using the formula, it is 2/3 raised to x all over ln of the base 2/3, which you will see here. And then now, we can evaluate the first integral, which is just negative 3 raised to u over ln of the base 3. So our integral is negative 3 raised to u all over ln of 3 minus 2/3 raised to x all over ln of 2/3 plus c. There's still a u here, so what do? We substitute back into x using the substitution rule here. So that means our integral, our final answer, will be negative quantity 3 raised to 1 minus x all over ln of 3 minus the quantity 2/3 raised to x all over ln of 2/3 plus c. And that's the final answer. So let's take a moment to digest the solution. Ready? Let's move on to the next problem. The integral of 3 raised to x minus 7 over e raised to 2x dx. If you want to solve the problem without looking at the solution first, you may pause the video now. I'll give you 5 seconds. This problem is a lot similar to the previous problem, problem number 8, in the sense that we can just separate the fraction again. And let's do that. So we have 3 raised to x over e raised to 2x as one integrand, and the other integrand is 7 over e raised to 2x dx. What do we do now? Remember that we can put exponentials in the denominator to the numerator by taking the negative of the exponent. So let's do that. The first integral becomes 3 over e squared quantity raised to x by the law of exponents. So notice we have now expressed this integral as a constant raised to just x. So we can readily integrate this using the exponential formula. For the second integral, we put the e raised to 2x into the numerator by turning it into e raised to minus 2x. First integral can be integrated readily. Second integral, we don't have a formula for that yet. But notice that our exponent for e is just negative 2x, which has derivative negative 2, which is constant. And remember, constants don't really influence our choice for u that much. They don't matter that much. So that means that our choice for u will be negative 2x. So du is negative 2 dx. So dx here becomes negative 1/2 du. I'm not gonna write it anymore so we can go faster. So the second integral becomes 7 e to the u times negative 1/2 du. We have eliminated all the instances of x here. Okay, let's evaluate both integrals directly already. We can do so in both cases. So the first integral becomes 3 over e squared quantity raised to x all over ln of the base 3 over e squared. And then the second integral, after a bit of simplification, let's put the negative sign, the negative 1/2 outside, and the 7 outside as well. So we have 7 halves e to the u. Its integral is 7 halves e to the u plus c. We have successfully integrated both integrals. What's the final step? That's right, substitute back into x. So our final answer should be 3 over e squared quantity raised to x all over ln of 3 minus 2. Where did this come from? This is just obtained from the laws of logarithms. So ln of 3 over e squared is just ln of 3 minus ln of e squared. But ln of e squared is just 2. So this is where the ln of 3 minus 2 comes from. Anyway, going back, 7 halves e to the u becomes 7 halves e to the negative 2x. And then plus c at the end. And this is our final answer. Let's take a moment to digest the solution. Ready? Let's move on to the next problem. E to the 3x over e to the x minus 5 dx. If you want to solve the problem without looking at the solution first, you may pause the video. I'll give you 5 seconds. First of all, this denominator is very annoying because it's not a single variable. So we might try to let u be e to the x minus 5 there so that the denominator just becomes u. But what about this e raised to 3x? What happens to it? Fortunately, e raised to 3x is just e raised to x and then cube. Factor out e to the x. Why do I do this? Because the derivative of e to the x minus 5 is e to the x dx. So this e to the x dx here becomes du. And then what's left? E to the 2x. E to the 2x is just the square of e to the x. That explains the e to the x squared here. So our candidate for u is e to the x minus 5. So du is e to the x dx and e to the x is u plus 5. What's the point of this? So that I can express this e to the x inside the square as an expression in terms of u. So applying the substitution, our integral becomes e to the x dx here becomes du, e to the x minus 5 in the denominator becomes u, and then the ex squared becomes u plus 5 squared. So now this is our new integral. Let's just expand. The square of u plus 5 is u squared plus 10u plus 25. And notice that this is just a rational function whose denominator is just a single variable u. So we can just separate the fraction, and that's what I'm gonna do. U squared over u is u, 10u over u is u, and 25 over u is still 25 over u. Now we can integrate each term directly, and let's do that. So integral is now u squared over 2 plus 10u plus 25 ln of absolute value of u plus c. So finally, we will substitute back into x. So u is e to the x minus 5. So our final answer is the square of e to the x minus 5 all over 2 plus 10 times the quantity e to the x minus 5 plus 25 ln of absolute value e to the x minus 5 plus c. So let's take a moment to take in the solution. Ready? Let's move on to the next problem. Integral of the quantity 3 to the x times the quantity cosine of 3 to the x minus sine of 3 to the x all over sine squared of 3 to the x dx. If you want to solve the problem first without looking at the solution, you may do so now. Pause the video. I'll give you 5 seconds. How do we start? Well, first of all, notice that there are so many 3 to the x there. And the derivative of 3 to the x is 3 to the x ln of 3. Ln of 3 is constant, so it doesn't matter as much. So that means that our u will be 3 to the x. But wait, let us first factor out the 3 to the x so that it's easier to see. And then, let us separate the fractions first. So we will have 3 to the x times the quantity cosine of 3 to the x over sine squared of 3 to the x minus sine of 3 to the x over sine squared of 3 to the x dx. That will be our integrand. The reason for splitting the fraction will be clearer later. Now let's apply our substitution. Let u be 3 to the x. Du is 3 to the x ln 3 dx. So 3 to the x dx, this one, and this one will be 1 over ln 3 du. And so the integral becomes, I just substituted all the 3 to the x with the u. And then this 3 to the x outside the parentheses will be combined with dx to become 1 over ln of 3 du. So why did I separate the fraction? Notice that I separated the fraction so that I can manipulate each of the resulting fractions independently. So the integral becomes 1 over ln 3 goes outside. So you have 1 over ln 3 times the integral of, I can separate the sine u in the first fraction. So we get cosine u over sine u times 1 over sine u. And then sine u over sine u squared is 1 over sine u du. And let's just write this in terms of the other trigonometric functions. So we will have 1 over ln 3 integral of cotangent u, cosecant u, minus cosecant u du. And we can use our formulas to integrate these two functions. So let's do that now. By the formulas, the integral will be 1 over ln 3 times the quantity, negative cosecant u, minus ln of absolute value, cosecant u minus cotangent u, and then plus c. So what's the final step? Final step will be substitute back into x. So the final answer will be 1 over ln 3 times the quantity, negative cosecant 3x, minus ln of absolute value of cosecant 3 to the x, minus cotangent 3 to the x, plus c. So let's take a moment to digest the solution. Let's move on to the final integral. Integral of the quantity 3 raised to the quantity log of cosine x to the base 2 plus secant x all over cotangent x dx. If you want to solve this problem without looking at the solution first, you may pause the video. I will give you 5 seconds. This is again a fraction with multiple terms in the numerator. So what do? We separate the fraction first. So we have two integrals now. The first one is the integral of 3 raised to the quantity log of cosine x to base 2 all over cotangent x dx plus the second integral, which is the integral of secant x over cotangent x dx. let's deal with the first integral first. What is our candidate for u? That's right. It's the annoying exponent in the exponential in the numerator, which is log of cosine x to the base 2. So let u be log of cosine x to the base 2. What is du? By chain rule, du is, let's put the cosine x in the denominator, multiply ln 2 because the base is 2, and then multiply negative sine x in the numerator. By chain rule, the derivative of cosine x is negative sine x. So du again is negative sine x over cosine x ln 2 dx. And let's simplify this. So we can put sine x in the denominator. It becomes 1 over sine x. Cosine x times 1 over sine x is cotangent x. So this expression simplifies to negative 1 over cotangent x ln 2 dx, which is here. 1 over cotangent x and then dx. And then ln 2 is constant. So we can now change the integral into an integral in terms of u. So we have the first integral becomes 3 to the u times negative ln of 2 du. Second integral is untouched. But okay, let us manipulate the second integral now so we can evaluate both integrals at the same time. Notice that we have 1 over cotangent x, but that is the same as tangent x. So we can simplify secant x over cotangent x as secant x tangent x. So the second integral becomes integral of secant x tangent x. And then this manipulation in the first integral came from just putting the constant negative ln 2 outside. So now we can evaluate both integrals right away. 3 raised to u by the formula integrates as 3 raised to u over ln of 3. And then we put the negative ln of 2 here. We multiply it to the integral. And then the second integral is secant x. That's because the derivative of secant x is secant x tangent x. And then we put plus c. So that's it. Or is it? Don't forget, you have to substitute back into x. So this 3 raised to u becomes 3 raised to log of cosine x to base 2. And let's just clean up the fraction a bit. So the final answer is negative quantity 3 raised to log of cosine x to the base 2 times ln 2 all over ln of 3 plus secant x plus c. Let's take a moment to take in the solution. Okay, to summarize, what have we learned? In the first part, for rectilinear motion, most of the problems are solved by solving for particular antiderivatives. In particular, velocity is a particular antiderivative of acceleration, and position is a particular antiderivative of velocity. And then, we will use the initial conditions of the problems to obtain the values of the constants we obtain when we integrate velocity and acceleration respectively. And then we will just plug in whatever value on position, velocity, or acceleration function depending on what the problem is asking to find the answer. So that's rectilinear motion. What about for integrals? As we can see, with the various number of examples here, there isn't really a clear-cut way to integrate, unlike in differentiation. There are some problems, such as number 1, where you can see the U-substitution right away. But in some of the problems, such as 8 or 12, you have to separate the fraction first and then look for a U-substitution. It's not as easy. So with that said, here are a few more problems for you to try out. I will flash them on the screen right now. Have fun! The integrals there are harder than some of the problems that we have discussed here. So, as an example, in number 4 and number 5, the u is not as easy to see. But good luck finding the u there. And that's it for our discussion class for today. See you next time.